All of the footage in this video has been declared unclassified by the Department of Defense and the Strategic Defense Initiative Organization. The footage you are about to see all comes from the Pentagon's official files on SDI. Our purpose here is not to enter into a political discussion, but rather to concentrate on the technological challenges of SDI and how the scientists and engineers are making Star Wars a reality today. In this first video on SDI, we will take a broader, more systems view of the total Star Wars architecture and how each piece must fit into the system.
I'm still optimistic that a way will be found. The door is open, and the opportunity to begin eliminating the nuclear threat is within reach.
When first announced in 1984, many people said it couldn't be done. The universal cry met by every new idea. But a few dedicated men and women in and out of the Pentagon believed differently. This is their continuing story. Before we begin, we should warn you that this video contains more acronyms than you can count, and a lot of jargon you may not understand. Acronyms are words formed by the first letters of a phrase, like HEDI, which stands for High Indo-Atmospheric Defense Interceptor. It speeds up communication, but if you don't understand the meaning, you're lost. To make it easier and save us the time of explaining things, we've included a complete printed glossary of SDI acronyms and terms with this video. SDI is extraordinarily complex, with literally dozens, perhaps hundreds of programs. We've divided the video into several major segments to help us understand and organize Star Wars. First, we'll look at the threat. Originally envisioned as protection from a massive Soviet attack, today's threat comes from regional and theater weapons in third world nations as well. In order to understand SDI, we need to understand the architecture of how a missile attack works and what kind of windows of opportunity exist during the 25 to 30 minutes from liftoff to impact. The character and vulnerability of an ICBM changes dramatically during flight as it goes from boost to mid-course deployment to terminal phase. At that point, we'll look at the history and background of SDI to put the whole program in perspective. Next, we'll check out the overwhelming challenge of ATP. In other words, acquisition, tracking, and pointing. Whether you're looking up into space with the sun as a background or down at the Earth with all its infrared interference, to find and track a target is very demanding. Then there's C-cubed. Command, control, and communications. With all the sophisticated jamming systems around, how do you keep in touch? Here's a hint. Use a frequency that can't be reached from Earth. After identifying the target, we'll look at destroying the missile and its warheads. As we look at Phase 1, we'll see how we went from smart rocks to brilliant pebbles, and how to hit a bullet with a bullet. In space, the delivery systems are unbelievably complex, but the warheads are kinetic. They carry no explosives of any kind. None. And finally, we'll take a look into the future at Phase 2. This is the real Star Wars. Speed-of-light weapons, neutral particle beams, ground-based lasers with free electrons using fighting mirrors, hypervelocity guns that accelerate to 10 kilometers per second at 100,000 Gs. Remember, everything you see in this video is real. It's happening today all over the world. From Lawrence Livermore Lab to Kwajalein Atoll. From Ground Zero, as the center of the Pentagon is called, to Edwards Air Force Base. The likelihood of a massive first strike from the Soviet Union is less today than in the past, but that does not eliminate the threat to American troops and interests in the world. Today, the greatest risk may come from the third world. There are 8 countries with missiles right now, and most have or are developing nuclear weapons. Afghanistan, Iran, Iraq, Israel, Saudi Arabia, South Korea, Syria, and South Yemen have missiles in service with ranges up to 2,700 kilometers. These other countries are testing or in development of missiles from North Korea's 300-kilometer Scud-B to Iraq's Tamaz-1 with a range of 2,000 clicks. As you can see, these missiles reach well into Europe. The CIA estimates that by the year 2000, over 15 developing countries will be producing their own ballistic missiles and arming them with nuclear, chemical, and biological weapons. The threat of massive U.S. retaliation may not be a great deterrent to some of the off-the-wall third world dictators. The only protection is a defensive one. You simply have to knock out the threat. Today, the United States has no active defense against missile attack. And finally, there is always the chance of an accidental missile firing. Today, it probably wouldn't lead to World War III, but as the old joke goes, a nuclear bomb can ruin your whole day. To defeat a ballistic missile, you have to understand how it works and how much time you have. The lifespan of a ballistic missile is only 30 minutes. In that time, it gets up and out of the Earth's atmosphere and goes through 3 distinctive phases. In the first phase, which includes both boost and post-boost, the missile is leaving a white-hot plume, and it's carrying all of its warheads in one platform or bus. A single intercept can take out all warheads with one blow. The problem is, boost only lasts 4 minutes, and post-boost lasts only another 10 minutes. Only 14 minutes to detect the launch, acquire the target, track it, and hit it. At mid-course, the bus, which carries all the warheads, releases up to a dozen live warheads and hundreds or even thousands of decoys. The trick, of course, is to distinguish between decoys and the real RVs, or re-entry vehicles. SDI has 13 minutes during mid-course to sort all that out. While most decoys are nothing more than mylar balloons, in the vacuum of space, they behave very much like RVs. To make matters really interesting, there's a good chance that all this will take place in a nuclear environment caused either as part of an enemy strategy or as the result of previous intercept. The RVs begin their terminal phase when they begin to pass through the atmosphere. In one way, that makes things easier. The atmosphere burns up and strips away all the decoys. But there are only 3 minutes left to impact, and the nuclear warheads are coming almost straight down at several thousand miles per hour. Put all together, SDI has less than 30 minutes to detect the launch vehicle, acquire the target, track it, discriminate the decoys, point, and fire. As early as 1984, SDI performed a successful mid-course intercept, hitting a bullet with a bullet. In 1985, SDI demonstrated that a laser could destroy a ballistic missile booster case. In 1986, as part of the Delta series, Delta 180 intercepted a thrusting target in space. As amazing as these feats were, in many ways, those were easy tasks. The real challenge is creating a system, not just a single technology. A system that cannot be overwhelmed or defensed with a single trigger. As with any research program, many ideas were explored in the early days. One possible solution would be the use of nuclear warheads, which, like horseshoes and hand grenades, only had to come close. There was the idea of huge lasers planted in space that could hit boosters, buses, and warheads with the speed of light. Both ideas have fallen out of favor. Nuclear warheads might create more problems than they would solve by generating an environment so alive with infrared and other energies and frequencies that nothing could be seen by SDI sensors and seekers. As for space-based lasers, in order to get the power needed for lethality, a space-based laser would have to be so big that the cost of boosting it into space in quantity would be prohibitive. Plus, having only a few such stations would make them vulnerable to enemy attack. So over time, SDI has become more streamlined and elegant. The need to acquire, track, and point at incoming missiles in all their stages, all their phenomenology, and against the background of space, the sun, the earth, and the Van Allen radiation belt has remained unchanged from the beginning. So has the need for massive, radiation-hardened, nuclear-hardened, jam-proof computers and communication. Phase 1, however, has come to focus on boost and post-boost, as well as mid-course defense. In both cases, we are looking at KEWs, or kinetic energy weapons. The KKVs, or kinetic kill vehicles, carry no explosive warheads of any kind. More on that later. Phase 2 focuses more on the mid-course and terminal threat through the use of DEWs, or directed energy weapons. These are speed-of-light weapons involving such technologies as neutral particle beams, free electron lasers, and chemical lasers. When you think of SDI, the first thing that comes to mind is impacting enemy missiles and warheads in space with bombs or laser beams. The biggest challenge to SDI may not be hitting a target. It's finding it and tracking it. ATP-FC is acquire, track, and point. That information is then converted to FC, or fire control. The first line of information comes from BSTS, Boost Surveillance and Tracking System. BSTS is a series of satellites looking down at the Earth. They are in geostable orbit, remaining over a single Earth point, 22,300 miles in space. A boosting rocket creates a large, white-hot plume that is relatively easy to spot and track. The tricky part comes in the handoff from the plume to the hard body of the missile itself. The tracking is of the plume, not the missile, so any kinetic or directed energy weapon must be targeted at the booster body, not the plume. A direct hit on the plume is worthless. As an ICBM sheds its boosters and becomes a bus, it loses most of its plume, but is still hot and still carries all of its warheads. Once out of post-boost, SSTS, or space-based surveillance and tracking, coupled with ground-based radar, take over and track right through the terminal attack phase. To accomplish simply acquiring and tracking an ICBM with multiple warhead missiles demands 4 major components. First, you have to pick out all the missiles from all the space and Earth backgrounds of visible wavelength and infrared wavelength. Second, you have to distinguish the missiles and especially the mid-course warheads from decoys and the over 5,000 satellites and other pieces of space junk floating around up there. Third, you need a computer system that is as fast as a supercomputer, hardened against radiation and electromagnetic bursts, and small enough to be boosted, powered, and cooled in space. And finally, you need a communication system that is jam-proof and secure, or the whole program will fail. One of the toughest target acquisition jobs is finding an object against the background of the Van Allen radiation belt, or the Aurora Borealis over the North Pole. If SDI could not find a target there, you can bet that's where all the attacking missiles would come from. As early as 1986, the Earth Limb program was measuring all the phenomenology of the Earth background, including the aurora. SDI has since proven it can find the target even there. The 9-month Delta Star flight conducted well over 100 operations measuring and mapping Earth and space backgrounds to be embedded in SDI sensor memory banks. It also collected the effects of various chemicals released in space as possible countermeasures. The Queen's Match flight of 1988 collected infrared data on foreign targets as SDI continued to build its database. In 1989, the Janus experiment used high-resolution infrared imagery to collect and catalog the signatures of post-boost vehicles so future SDI sensors could compare what they are observing to a database of known phenomenology and recognize what they are looking at. Distinguishing decoys can be tough, but not impossible. The first step is to discover the different signatures of warheads and decoys. The Delta 180 series has been collecting information and helping build a database of vehicle and decoy signatures. Another way to distinguish warheads from decoys is interactively. SDI is testing methods of hitting both decoys and warheads with broad-beamed, low-power lasers. The heavier, dense warheads will absorb the laser energy and become warm or marked, while the laser energy will pass right through or destroy the decoy. Weapons guidance systems and seekers can then go only to the warmer marked targets. SDI computing capability has grown and shrunk at the same time. SDI needs supercomputer-style capacity in space, but can't spare the room, weight, or power. While space-based computers don't need the memory, they do need the speed. Comparing a BP flight computer with a Cray-1, we see the BP has 1/3 the MIPS, or millions of instructions per second speed, but it weighs 3 pounds compared to 10,000 and uses only 28 watts of power compared to 100,000 watts for the Cray-1. SDI is working on diamond-based computer chips compared to the current silicon-based chips. Diamond chips can take operating temperatures of 500 degrees Celsius compared to 100 degrees Celsius failure temperatures for silicon chips. This means that future SDI computers can be totally solid. No need for space to cool chips. Even at the speed of light, less distance to travel means faster processing. Space-to-space communications will probably be at 60 gigahertz. This ultra-high frequency has two major advantages. It is out of the range of nuclear effects, which are frequency-dependent. 60 gigahertz is also less susceptible to Earth-based jamming. The 60 gigahertz signal, and therefore any jamming signal, is absorbed by the oxygen absorption line in the Earth's atmosphere. It would never reach space, but would be absorbed. This space-to-space communication also points to another critical feature of SDI, independent operation of weapon systems. If one part of the entire SDI system fails or is destroyed, the others must proceed as instructed by themselves. Phase 1 weapons are all kinetic kill vehicles. The two systems are brilliant pebbles and ground-based interceptors. GBI focuses on mid-course or exo-atmospheric RVs and will be fired from CONUS bases. In 1987, the FLAGI, or Flexible Lightweight Agile Guided Experiment, successfully intercepted a theater-type missile re-entry vehicle using a radar-guided interceptor. Between the 1984 hitting a bullet with a non-nuclear bullet test and the 1987 FLAGI test, the problem became less hitting and destroying the target than finding and seeking the target. ERIS, or Exo-Atmospheric Re-Entry Vehicle Interceptor Subsystem, will test all the issues created by a mid-course intercept, including optical seeker, divert, and axial propulsion, all under stressing conditions. One of the keys is to eliminate the effects of GBI's thrusting environment as it streaks up through the atmosphere seeking its mid-course target. While other sensors in SSTS and GBR, or ground-based radar, may locate the target, onboard sensors must function in order to allow any GBI to seek and destroy its target. This is done primarily with infrared seekers. Initial validation tests will be conducted using a standard Minuteman I ICBM with a KKV mounted as the payload. In its operational phase, the GBI will be smaller than the second stage of a Minuteman. The ERIS kinetic kill vehicle carries all its own systems, including avionics, divert propulsion, infrared seeker, and kill enhancement device to improve lethality. The first full ERIS test flights are scheduled for 1991. The heart of SDI Phase 1 will undoubtedly be brilliant pebbles. It is smaller and smarter, hence the move from smart rocks to brilliant pebbles. As a kinetic kill vehicle, BP carries no warheads. Its mission is to find and destroy boost and post-boost enemy vehicles simply by running into them, like throwing a rock at a bottle. At the incredible closing speeds of a BP vehicle and a boosting rocket, over 14,000 kilometers per second, the two simply liquefy and literally pass through each other. Since the time window to acquire and track a boost or post-boost vehicle is so short, any first-layer system must be space-based. There isn't time to get it into position. It must always be there. Red team, blue team countermeasure analysis has shown the singlet system to be the most effective. While packing up to 12 brilliant pebbles on one station would be more efficient, it becomes a meaningful target to an enemy in much the same way a post-boost bus is. When the system is deployed, brilliant pebbles will consist of 4,067 individual weapons poised in space, ready to strike. The cost of destroying a singlet system approaches the cost of a nuclear attack by an enemy. It's just not feasible. Once the attack command is issued, Brilliant Pebbles is self-contained and independent. Each pebble carries a life jacket to protect its computers and components from radiation, and the whole unit from space dust and debris. The jacket also contains the solar array to power the weapon while it sits quietly in space, waiting to strike. Since a geostable orbit would put the pebble too far away to get to its target in time, each pebble has a star tracking system which monitors its location at all times. Its own tracking and communication systems allow BP to find and attack its boosting and post-boost target independently and ensure that each pebble attacks a different target with no further information from C-cubed once the release command is issued. One of the most significant SDI tests to date was the full-duration flight test of a space-based interceptor soon to become Brilliant Pebbles. This hover test brought together all the elements of acquisition, tracking, control, and independent operation. This vehicle is tracking a heat source similar to a boosting rocket on the other side of the wall. It is operating totally on its own. One of the most exciting moments is when the system handed off the plume to the missile hard body for final lethal intercept. While it must remain in space indefinitely, the active life of a Brilliant Pebble is under 30 seconds. At the end of 1990, another hover test was successfully conducted. Here, the vehicle, with all its controls and lethality, is tiny compared to the first test vehicle. This miniaturization reduces the cost of boosting into space and makes a Brilliant Pebble truly a pebble and much more difficult to find. SDI Phase 2 consists of programs and systems with longer lead times and more technology challenges. They are designed to provide layers to SDI. A layered, multifaceted series of defense systems is the heart of an SDI strategy. Knocking out or countermeasuring any one system does not render SDI ineffective. There are 2 kinetic weapons and 3 speed-of-light weapon systems. Head-eye, hypervelocity gun, neutral particle beam, space-based laser, and ground-based laser. Head-eye, or High Endo-Atmospheric Defense Interceptor, is similar to Phase 1 GBI. Only Head-eye strikes RVs in terminal phase, just after any remaining decoys are stripped away by the atmosphere. In an ideal situation, Head-eye would not be needed, because all warheads would have been destroyed in boost or mid-course. The hypervelocity gun, or HVG, is in some ways the simplest weapon. A very, very high-speed projectile fired from space or ground through electromagnetic acceleration. Neutral particle beams have been propagated on Earth for some time. They are immensely powerful, but the real question is, how will they behave in the vacuum of space? And can the accelerators and power systems be made small enough to be put into space? Laser weapons are both ground and space-based. Right now, the space-based laser may be the most effective in the interactive discrimination of targets from decoys. They would be chemical lasers. Ground-based lasers can get all the power they need. There are no real size limitations. The challenge is to get the beam into space through the atmosphere and direct it to a target. The first Head-eye flight test was conducted January 26, 1990. It lasted only 7 seconds, but it proved a lot. At the very high speeds achieved by Head-eye, at least 7,800 feet per second, Both the bow wave and heat at the nose tip of the vehicle can make the seeker's sensors unreliable. A cryogenic cooler is sprayed over the LWIR window. This instantly reduces the temperature to 100 degrees Fahrenheit. While all the attention in SDI is focused on the weapons and kills themselves, without something as seemingly mundane as cooling a seeker window for just a few seconds, there could be no intercept, no high-impact, high-visibility effect. Imagine firing a hockey puck so fast it will penetrate 1 inch of tempered steel. That essentially is an HVG. It's like a machine gun, only the bullets are accelerated not by a chemical explosion, but by electromagnetic acceleration. The acceleration is 100,000 Gs. That's right, 100,000 times the force of gravity. To put it in perspective, a fighter pilot maxes out at about 10 Gs. HVGs can be space-based or ground-based. The launch velocity of a space-based gun would be about 10 kilometers per second. A high-powered hunting rifle carries a muzzle velocity of 2,900 feet per second. HVG muzzle velocity is over 32,000 feet per second. You can see what it does to steel plating. Imagine what it can do to the thin skin of a ballistic missile. Neutral particle beam is one of the more exotic SDI systems. It works primarily by totally scrambling the control and computer systems of the incoming missile or RV. A neutral particle beam is a stream of highly accelerated negative ions. The technology has been around for years. In fact, one promising approach is the Soviet-developed RFQ, or radio frequency quadrupole system. Its chief advantage is its lightweight. NPB can also be used to mark or paint warheads and allow other kill weapons to distinguish warheads from decoys. A major challenge is to reduce the size of NPB accelerators so they can be boosted into space and to generate the kind of power needed. Accelerator size has been reduced substantially, as you can see, but it is mandatory that power in the range of 50 MeVs be maintained. That's 50 million electron volts. The Bear test, launched on July 13, 1989, was the first successful operation of a directed energy weapon in space. It proved that directed energy can be reliably operated in space. The future of space-based SDI lasers is found in the Alpha laser, which became operational in April 1989. This is a chemical-based laser. It has the advantage of low power consumption and smaller size. Space-based lasers have the further advantage of no atmospheric distortion and can go straight line to the target. With lethality demonstrated, the next major step is beam control and pointing. As the old joke goes, it's all done with mirrors. The LAMP, or Large Advanced Mirror Program, is designed to achieve this. When operational, LAMP will be several times larger than the Hubble Space Telescope. Even if full lethality is not achieved with a chemical space-based laser, its ability to destroy decoys, especially balloon decoys, thermally tag warheads, and create a velocity change signature on the warhead will make kills by other layers of SDI easier and faster. Ever since an atmospherically corrected laser tracked a booster rocket in 1985, the ability to propagate a laser beam from the ground into space seemed feasible. Laser light is absolutely parallel. A distortion in the atmosphere, like the wavy shimmering you see looking out over the road on a hot summer day, reduces the laser's effectiveness. SDI computers are now calculating the distortion in real time and adjusting the mirror to compensate for such distortion, creating a true and effective laser beam as it emerges from the atmosphere. In February 1990, a Delta II launched both LACE and RME into space. LACE is a 2.5-year low-power atmospheric compensation experiment to further refine beam distortion issues. RME will demonstrate the ability to reflect a laser beam from a space mirror and point to a target. Such a target may be a series of fighting mirrors, which in turn will divide the beam and aim multiple beams at multiple targets. GBL is not limited in power due to boosting weight limits. One of the more promising paths for ground-based lasers is FEL, or free electron laser. Electrons are jarred loose from their atoms and fed as bundles or electron bullets into a laser beam. Such an approach increases the lethality of the beam while offering the possibility of lower power consumption. This translates into more lasers at the same cost. In this video, we attempted to give you an overview of SDI, only outline its many successes, and look at some of SDI's more interesting systems. Over the next 12 months, a significant number of SDI systems will be tested in a series of VAL-DEM, or validation and demonstration tests. These tests will focus more on full systems and system integration and less on components than in the past several years. Some of the experiments for 1991-92 include the first Brilliant Pebbles intercept, the 60mm hypervelocity gun, the first LEAP, or lightweight exoatmospheric projectile intercept, the first ARIS mid-course discrimination and intercept, the first head-eye intercept of a terminal RV, the first mid-power neutral particle beam demonstration. This one is still on the ground. And finally, the first full-power free electron laser beam demonstration. We'll track all the activities and more and issue our findings in the next